do these three problems together. Alright, how do we attack this first one? Dylan?
First, we're going to multiply 4a to the fourth times b squared times 2a squared times b, and it'll be 8a to the sixth and b to the third. And then we'll have negative 8a to the sixth and b to the third. And it's essentially just going to be negative 16 to the sixth.
Good. Okay, in seeing these, we're using your exponent properties. Right? Saying, all right, this is 2 to the third. We're multiplying that exponent, multiplying this exponent. Here we're multiplying across, so you're adding the exponents. Okay, multiplying the 4 and the 2. Then you're multiplying a to the fourth, a to the second. A to the fourth times a to the second is a to the sixth. You're adding the exponents. Good. So then we have like terms, and we can combine from there. David?
Is that b to the third?
The last one?
Yeah.
Yeah, b.
Yeah.
Not a six. B to the third. The negative 16, a to the sixth, b to the third. And then we have 6. Okay? All right, how about for the second one? What can we do for the second one? Where do we go? Justin?
Begin by multiplying x plus 3 times x minus 4, and you get x squared minus x minus 12.
Good.
And then you can write out the x plus 2 squared by x plus 2 times x plus 2.
Good.
So you get x squared plus 4x plus 4. And then you subtract that from your first answer, you get 3x minus 8.
Okay, so when we subtract this, what do we have to keep in mind? The negative. Distributing the negative. So even though you're expanding and multiplying it out, you're still going to have some grouping symbols around that second polynomial. Now when we go through, you have x squared minus x minus 12, and then minus x squared minus 4x minus 4, so negative 5x. So you get negative 5x minus 16. Okay? That's going to be important with these. Making sure we know where to place the grouping symbols, and if we are subtracting, making sure that we're adding the grouping symbols where we need to remind ourselves that we have to distribute. Okay, something that still needs to be cleaned up. What does this equal? Jason, how did you get that?
You see that with 2 parentheses are the same on each side, and then when you just distribute the negative on the right side, you just subtract the same.
Yeah. Isn't it x minus 7 times x plus 8 minus x minus 7 times x plus 8? Do you have to do anything besides state it's 0? No, but you have to read the whole problem. Don't automatically look at the problem and be like, ooh, great, I can use the FOIL method. Ooh, great, I can use the FOIL method, and then I can distribute. And then when you get to 0, you're like, oh, well, what if I just took a moment to read the problem? Okay? So make sure you're reading the problem, seeing what it's asking of you before you're jumping in to multiply everything. Okay? Good. All right, so we're going to talk about some polynomial functions today. So we talked about polynomial expressions yesterday. Polynomial expressions. We have expressions that can be simplified. We have functions that can be solved, that can be graphed. So polynomial functions of degree 2 or higher have graphs that are smooth and continuous. So we're writing this down. Have graphs that are smooth and continuous. And we've looked at graphs like this before, and I think yesterday some of you were like, oh, these are the graphs that like go up and down, up and down, up and down. And I said, yes, that's what we're going to be looking at. So is a quadratic a polynomial function? Does it fall under that category? Is a quadratic a polynomial function? Yes. It's a type of polynomial function. It has a graph that is smooth and continuous. So by smooth, we mean the graph contains rounded curves with no sharp corners. Okay? And by continuous, we mean the graph has no breaks at all, and it can be drawn without lifting your pencil. So we've seen quadratics. A quadratic is a continuous function. I just did a nice big U shape, didn't have to lift my pencil. Another example of a polynomial could be something like this. Right? You could draw this curve without lifting your pencil. What have we looked at this year that is not continuous? Piecewise functions. Right? Piecewise functions. We have a piecewise function. We had breaks in our graph. I had to lift up my pencil to draw this graph. So this is non-continuous. So we need to pick up our pencil. Okay? So we have smooth graphs. And we have continuous graphs for polynomials. Yeah.
Is a linear function also like is like can this be, is it like I don't say it, like does the same rules or no, like because it's like there's no breaks.
There's no
sharp
breaks,
corners.
no sharp corners, but it doesn't have curves in it. So a linear function is itself its
Not
own
polynomial.
type of graph. A quadratic, however, is a type of polynomial. What's the degree of a linear function?
2.
Of a linear function?
Oh, yeah, you're right.
1. So the degree of a linear function is 1, so that does not fall under this category.
It's just mx plus b.
Yes, y equals mx plus b, so the x has a degree 1. Okay, so that's its own separate type of graph. But yes, linear functions are continuous, aren't they? Are absolute value functions continuous? Yes. But would they fall under this category of polynomial functions and absolute value functions? Well, sometimes you can have a degree, you can have a higher degree, but are there going to be corners in absolute value graphs?
Oh, yeah.
Yeah, right? It's at V.
Oh yeah.
Remember, that's a corner point. So anytime you see a graph that has a corner, this is a corner point. Right? It's the bottom of that V. So, I want us to think about this function. Yikes. Wowzers. Negative x to the 7th over 100. Don't write this down, just look at it. Plus 3, x to the 6th over 25, yada, yada, yada. What do you know about this graph? Is there anything that you know about this graph, Jack?
Well, I know you can have it on the calendar easily.
Totally. What do you know, though, about this graph? Any key things that we could point out, Dylan?
Degrees more than 2.
What is the okay? The degree is more than 2, so
Seven.
it's 7. So it's a 7th degree polynomial. Okay. So the degree is more than 2. It's a polynomial. So we know there's going to have some curves to it. All right. We know it's going to be continuous. What else do we know? Or did you your hand up? What else do we know?
It opens down.
Okay, so we have a negative in front. For quadratics, we can say that it opens downwards. But is this a quadratic function? No. So we're going to look and see today what this negative does in a polynomial function. It is going to do some reflecting somehow, but we're going to see what it would look like. Anything else that you know about this?
They all have.
It doesn't have a constant. So what does that mean? There's no C term, okay? So what is that? Doesn't cost. It will, but at which point? 0. We know that it has a point 0, 0, because that's our y-intercept. So 0, 0 is our y-intercept and one of our x-intercepts. Okay? Yeah.
I don't know how we have more than 2 x-intercepts.
Probably. All right, so ready? This is what this graph looks like. Is that a continuous function? Yeah. Is that a polynomial function?
Yeah.
Okay. Now, We have 0, 0. Yes, 0, 0, that's a point on the graph. And then we have all these other things happening. This is the equation that I had on the previous slide, written in which form?
Standard. No, just kidding.
You did this last unit in quadratics.
Shorthand?
Don't just start shouting out random forms, think about it. Intercept form. Remember when we graphed in intercept form? Okay, so we know that. What do you notice? Look at the binomials that you have within these factors. What do you see from the equation to the graph? Anything that you notice?
There's an x minus 4 and it's on the floor.
What's that?
There's an x minus 4 and it's on the floor.
So we have a point here at 4. Okay. What else do you notice? Really?
The x time when x is 0, then the 1 would be 0 because of the negative 1 over 100.
Yeah, so we have this origin point, 0, 0, right? We saw that from before. Sydney?
You have an x on the minimum and on 2.
We have an x at negative 1 and on 2. Look. And where is it? There. This is x plus 1 squared. When we saw this in a quadratic, what did we... What did I say? We saw it was what? Can you stop the clicking? We saw what? It was a parabola. Look at what happens here. What kind of root would x plus 1 squared be if we were just to graph y equals x plus 1 squared? A double root. Does this cross the x-axis at this point? It just touches it. It bounces off the x-axis. So we have a double root right here. And you know what? We have a triple root right there, which does something different to the graph that we're going to explore. So by the end of this unit, if I gave you this equation, you'd be able to graph all of this. You would be able to graph all this. That is our goal, is to be able to graph something this crazy, wacky, and wild.
What does this graph tell us? Like, what could this graph potentially tell us?
It could, I mean, there's parts of it that like have quadratic trends, right? Here, here. So it's just like connection of everything. I don't know, this is just a random problem. Probably won't be this complicated, but there are models that we'll look at that should have polynomial trends. Okay. Just like we had quadratic regression, there's also polynomial regression.
Like, will this have like real world applications? Like, could it be a work
Yeah,
This particular problem?
and stuff like this?
Could potentially. There would have to be a lot of variables and other fact, like information involved in it. Alright, so we're going to talk about recognizing the general shape of each function. We can generalize how this graph will look. So what does f of x equal x squared look like? What is it? What is it a graph of? A what? It's a quadratic. It's a parabola. So here we have a parabola. How about negative x squared? What will that look like? David? Yeah, so it's going to be flipped downwards over the x-axis. Good. I want everyone to make a t-chart, and I want you to think about or draw what f of x equals x to the third looks like. I may have done it a while ago. Haven't looked at it in a while. So try this out. Just a general graph. You don't have, it doesn't have to be exact, but I want you to see what the graph looks like. So if we're plugging in -2 into this function, Justin, what's our
It's gonna come
output?
out as a negative number, so it's gonna be 8.
-8. Okay? How about for -1? We'll get
-1.
0 at 0. For 1 cubed, we'll get
1.
For 2 cubed, we'll get
8.
+8. So this graph looks like this. This is a cubic function. Okay. So when we looked at our quadratic, when we had a -x squared, we flipped it down over the x-axis. What do you suppose is going to happen here? We're going to start at the top left and go down to the bottom right. So you're still reflecting it. Okay. So these are cubic functions. Cubic functions. Let's get my graphing calculator. Graph. What's our graphing calculator called? TI. Thank you.
TI Inspire TI.
Gotcha. Okay. What do you suppose f of x equals x to the 4th is going to look like? What do you think? X to the 4th. What do you think that's going to look like?
I guess it looks something like a parabola.
It would look something like a parabola. Would it be at a higher point? So if I graph y equals x,
Like -2 reduced it.
so it's going to get higher up much faster.
Yeah.
Okay. Yes. What do you think?
Would it have 3 curves?
Would have 3 curves? Maybe. If y equals x to the 4th, I have something that looks like this. How is this ending? What do I mean by that? How is the graph ending? If I were to raise the question like that.
No, it would never get
Which
zero.
direction is it ending? Which quadrants is it ending? 1 and 2. So on the left it's rising, and on the right it's rising. So what if I were to do negative x to the 4th? Flip down. So now we're downward facing again. What if I said x to the 6th? What would that look like?
Same thing, but possibly even closer.
Same thing, meaning what? Same thing.
Same kind of like. I mean, I don't have a clue.
No, but I want you to
But
just.
same kind of like parabola-looking thing.
Okay. So if I now said here x to the 6th, did it change? It changed a little bit, right, of the blue line. But how is it ending still? Which quadrants is the graph reaching up towards? First and the second. What would x to the 10th be? How would that change? How would the graph be ending in the first and second quadrants? Would it be going up or would it be going down? Up still. Okay? What would get increasingly smaller?
Yeah.
We get thinner?
Yeah.
Or we get
Want to
wider?
get closer to the line?
Thinner.
We're going to talk about that.
The lane,
Wait,
like the
what
lines
was
get
it?
like straighter.
All right, what would x to the 5th look like? What x to the 5th look like? X to the 5th looks like this. What does it look like? It looks like x to the 3rd.
So it's always gonna look.
To the odd
Some-
rows.
So it's always going to look like the quadratic, or it's going to look like the cubic. What do you suppose negative x to the 5th will look like? It would look like negative x to the 3rd. So we're generalizing what these graphs are going to look like. Let's look back at this big, wacky example. Okay. Arden said, okay, we have this negative. What's the degree of this polynomial, Arden? 7. Is that an odd degree or an even degree? Odd degree. So it's an odd degree. It will follow the same trend as the cubic that we just saw. So let's see if that's what it's showing.
Oh, so it's odd.
Oh, so it's a negative, and it's a cubic, right? It's finishing like a cubic function would finish. Do you see that? So, this is called end behavior. We can figure out the behavior of a polynomial function if we're looking at the far left of the graph or the far right of the graph. So the end behavior depends on the leading term. And the leading term is always the term with the highest degree. So when we write expressions in descending order, we need to write polynomial functions in descending order as well. Going back to that negative x to the 7th over 100 example, right? It was negative, and with the highest degree of all the terms was the 7th degree. So now that we know what the degree is and whether it's positive or negative, we can generalize how this graph will begin and how it's going to end. So another way we can think about it is, like the first bullet point, the behavior of the function to the far left or the far right. So you're looking at the behavior of the function when x is really, really negative, close to negative infinity, or on its way to negative infinity. And then to the far right, you're looking for what's happening to the graph when it's really close to positive infinity. Okay? How do I write this? Far left. Okay? So, left behavior and right behavior. Left behavior is actually telling you, all right, if I'm looking to the left of this graph, where x is really small, x is getting closer to infinity. When x is getting closer to negative infinity, and the degree is even, and your leading term is positive, think about the degree. Right? If your degree is even, how did we say the graph is going to finish? Point with your fingers. How's the graph going to finish? It's going to finish like this, like this, like this, or up? Up in both directions. So if your degree is even and it's positive, you want to think about x squared and what that looks like. So if the degree is even, you're finishing upward. Upward on the left, and then right behavior is upward on the right. So you're using arrows to indicate the behavior. Okay? So the right behavior, when x is getting closer to positive infinity, it's either going to go up or it's going to be going down. So if the degree is even and negative, how is that going to fade? How is that going to look? Down, right? So we're going to think of negative x squared. On the left it's going down, and on the right it's going down. That's how the graph is finishing. That's how the graph is ending in both directions. If the degree is odd and positive, we need to think of which function. X to the third, right? Think of x to the third. And on the left of that graph, it was going where? Down, and on the right, it was going up. If the degree is odd and negative, we need to think of negative x to the third. And towards the left, it was going up. And then to the right, it's going down. So you can use arrows to indicate the behavior, but you know this is how the graph is going to end. And then there could be all this other stuff happening in between. But you know that it's going to be ending up, up, down, 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 up, or up, down. Okay? So if we know the end behavior, and we know the roots, right? If we have intercept form, then we can pretty much figure out what this graph would look like. Questions with this? All right, so let's practice figuring out what the end behavior would be for surf graphs. Okay. Determine which of the graphs most closely resembles the graph of 5x to the third minus 6x squared plus 2x plus 3. So what do you know about that graph? Sydney?
The degree is odd.
The degree is odd. And it's positive, so odd degree. So it's going to look like x cubed. So it's a positive odd degree. So it's going to look like x cubed. Which of these looks like x cubed? B. How about the next one? Negative x squared plus 3x plus 6. Which of these graphs would most closely resemble this function?
Oh, wait, sorry. It's even, and is it A? Oh no, it's C because it's reflected.
It's reflected downward. So if you think about quadratics, we know they're downward facing. If that A term in front is negative and the degree is 2. Right? No, it's finishing down, down. All right, let's look at something a little bit different. Okay, I want everyone to write the end behavior for these two. Think about these two problems. So use arrows to indicate the direction. So let's write the problem down so we know what it was we were looking at. So our goal is to find what first? What's our goal when we're looking at this function? What do we have to figure out? Find the degree of the polynomial. What's the degree of this polynomial, folks? 3. It's the highest degree of its terms. It's a third degree polynomial. It's an odd degree. Also, what do we know about this leading term? It's negative. So we want to think of negative x to the third. How is this graph finishing? What's the end behavior of negative x to the third? Jack?
It's going down. It's going down and up.
Down, then up like that?
Yes. Oh, no, wait, I'm sorry, that's not it.
So
It's up and then...
up to the left, down on the right. How about for number 2? This is written in a different form. But can you figure out the degree? What's the degree, Sid? 4. How'd you get that?
Because it's the third degree there, and it's
1. It's to the third degree there. How do you figure out the degrees when you have something in factored form? You count up all of the x's. So you have 1x here, and we have 1, 2, 3 x's here because it's to the third power. So this is fourth degree. And is this a positive function or a negative function? Is this a positive function or a negative function? Positive. So how is this ending? What's the end behavior, Willie?
It would be up.
Up, up. Okay. Can we graph this? If we know we have roots at 4 and at 3. Okay. Yes? And we know we're finishing up, up. What's our y-intercept? How can we find our y-intercept? Really?
It would be negative 27 times negative 4. And that is 1.
So, positive. So we know we have to come down this way. We know we have a triple root. Oops. Let's finish up, up. Okay. So we're gonna get to this. What?
It's 1 or 2. 1.
This is 2.
Like, I'll put the triple root once we go down and back up.
Because you know the end behavior is up, but you have that up. And you know you have to go through 3, and you know you have to go through 4.
So does 3 represent the triple root?
Yes. But a double root is different from a square root. So we're going to talk about this. Try these two. Figure out the end behavior for number 3 and number 4. So what do you think? David?
For number 3, I based it off of like 4 x 15, that's what was the highest degree term.
Good, the highest degree term may not always be given to you listed first, so you have to read the whole equation to figure that out. So what would the end behavior be here?
It goes like that.
It goes down to the left and then up on the right. Good, because if it's positive, it has an odd degree. It's going to follow the same rules at positive x to the third. How about for number 4? For number 4. What do you think, Liza?
1 is the degree.
104 is the degree, so this term, yeah?
It's even, and negative, so it's kind of like a reflection of x squared.
Good. It's going to follow the same trend as the negative x squared. So making sure that you're reading that, see what the degree of the polynomial is, and you can figure out the end behavior, and then fill in everything else that you find along the way. I want everyone to try this problem, and then I'll hand out your homework.
Are you asking x plus 1 or?
No, I think a plus 1.
Oh.
How do we find f of a plus 1? Jason?
Plug in
Good, so we have a plus 1.
squared
do we simplify this?
Foil 1 squared, you get a squared plus 2 equals 1. 5a plus 5 plus 2. That's going to be a squared plus 7a plus 4.
Just making sure that we're remembering how we're plugging in these expressions. Okay? Alright, so I have a homework worksheet for you. It's about 8 minutes. Where do you start your math? Okay, let's remind ourselves. I lied. You're being so good today, so we're just going to get so much done. Okay, the homework's short. It's not going to take you very long. Don't worry. All right, so methods that we had for factoring. We have 2 more factoring methods that we're going to look at today, or maybe next class as well. Okay. So we have done the greatest common factor, trinomial factoring, perfect square trinomials, difference of 2 squares, variable substitution, and then we need to still look at grouping method and the sum and difference of 2 cubes. Okay. So let's remind ourselves how we complete the greatest common factor method when we have problems like this. What do you remember of the GCF method of factoring, Willie?
It would be like.
What's the greatest common factor of this expression?
X minus 5.
Yeah, so this expression, this binomial, is the GCF. So if we factor that out, what is left, Willie?
You get x minus 5 times 2 plus 3.
Great. How about this expression? What is your GCF? David?
X squared plus 5y.
Okay, good. That's a common term, or common binomial in both of these terms. So if we factor that out, what's left?
X squared plus 5y times.
Good. That -1 we got to keep there. Good. So now we have this grouping method, and many of you have probably seen the grouping method before. We just didn't do it in our quadratics unit because you need a degree higher than 2 in order to use the grouping method. So now that we're in polynomials, it fits nicely. Grouping method. Okay. Grouping method is used primarily when you have 4 terms. Grouping method is used primarily when you have 4 terms. Here's how the grouping method works. Grouping method. What do you suppose that we have to do if we are grouping? Jason. Okay, we are going to group 2 terms together. Now it's the GCF method. What's the GCF in this first group, Jason? So what's left? Okay. What's the GCF in the second group, Jason? And what's left? Don't we know how to factor this now? Wasn't this the previous problem? Yeah? What's the GCF?
So how do you know which pair to group? Could it be in any order?
Yes. Could be in any order, because you could have x to the third plus 3x plus 5x squared plus 15. And if you group this way, you're factoring in x, okay, x squared plus 3. And here, if you're factoring out a 5, you have x squared plus 3. Oh, perfect. X plus 5, x squared plus 3.
So no matter what order.
Okay. So let's use the grouping method over here. So if we group, what's the GCF in this first group? Willie?
N squared.
And what's left?
N squared.
Plus? What? What's the GCF here? -2. So we factored out a -2 because our goal is to make these expressions the same, so that we can do that bigger grouping method. Yeah.
But what doesn't the sign in the middle go from 1 or the end over?
Like in that one.
So this is the plus a negative 2n squared. So you're looking at it differently. Okay. So now your GCF is n squared plus 1, and what's left? N squared minus 2. The grouping method. How many of you have seen this before?
We did this right in here.
We did this.
No.
Like, like briefly, we did. I know for, I remember it.
Well, we did this step,
There's a question like
Yeah, this time.
but we didn't do this one.
Oh, yeah.
It was different.
But it's something like this for equivalence.
Was that led you before?
That's variable substitution. Yeah, that's different. It is variable substitution, but it's called the grouping method. Okay, because from the start you have the 4 terms, and you're going to get down to the 2 dimensions. Okay? So, grouping method. We'll review this again next week, but then we're going to be moving on with some other problem types. Okay? So, homework is a worksheet. Again, it is not the longest worksheet. Okay. Okay, is everyone have one?
Yes.
Wonderful. I suggest studying or making sure if you didn't check your homework from last night, check it this weekend. Understood? We would see each other next Wednesday and then next Friday. We don't meet next Thursday, just in general for the week that we have. All right, so I'll see you all on Wednesday.
Thank you.
Have a good one. Thank you. You're welcome.